This is a position time graph. What a position time graph represents is how far an object has traveled in any given time. So for example, if I look at time 6, the object has traveled around 12 meters, if I give it a unit of meters. So it shows me how far an object has traveled in any given time. Now, if I look at this time right here, or this point right here, and ask myself, what time, like how far this has traveled. This is what you call an instantaneous position. An instantaneous position. So the location of an object at a certain given time. So what else can we know and what else can we tell from this graph? Well, one, we can look at the line here, and since it's a diagonal line, or a linear line diagonally, we can tell that it's moving in a constant motion. So it's continuously moving at a constant rate. Now, the slope, if we were to calculate the slope of this line, so it would be rise over run, it would tell us the velocity of this object and how fast it's moving. Now, we mentioned before that the slope of a position time graph represents the velocity. So slope is equal to the velocity of the position time graph. So if I wanted to calculate the average velocity, then in between two different points, so let's say point A and point B, I would have to calculate the slope. So for example, in this case, the slope would be rise over run. So 16 minus 8 over 12 minus 4. Now, you can calculate this. It would be 8 over 8, and you would get 1 meter per second. So this is the velocity of our object right here. The average velocity of our object here. Now, if we look at this position time graph here, we have a curved line. Now, whenever we see a curved line, we know immediately that it's to the second degree. So it's exponential. So degree would be here 2. Earlier in the graph, we had a straight line. So immediately we consider it or not a straight line, but a linear diagonal line. So immediately we can consider it degree 1. Degree 1. Now in this graph over here, the object isn't in constant motion, unlike in the linear line. It's curved, meaning that the object is either speeding up or slowing down. However, in this case, it's slowing down. Now, why is that? Well, if we look at the object, we can tell that at 2 to 4 at seconds 2, it's moving at around 8 meters. It reached 8 meters in around 2 seconds. However, if we look at second 4, it moved around less than 16 meters in around 2 seconds again. Now, in another 2 seconds, it moved around another 3 meters. So just by reading the graph, you can tell that it's slowing down, and eventually it'll reach a stop here where it won't move at all. It won't move at all, and it'll just stop moving. Now, when in its position time graph it stops moving, the graph would look something like this, where here you have your xt graph, so t and x, so in meters. So it's just a straight line where the position, so if this is 10 meters and the time is going by, it doesn't change. So at 2 seconds it's 10 meters, and at 8 seconds it's still 10 meters. 10 meters. So it's not moving. Now, when we look at this, when we look at this slowing down graph, how do we calculate the speed at any certain time? So if I were to ask you right now, what is the speed at second 6? So I would so at this point right here, how would I calculate the speed at this point? So the speed at this point. Well, there's a simple method to doing this, and it's by drawing a tangent line. A tangent line is a line that intersects any curved line at only one point. So in this case, it would be the t equals to 6 point. So we draw just a tangent line here. Now, to calculate the average speed here, we simply find the slope of any point from this line. So if we were to calculate the slope here, it would be, so we can use second 4 as point 1. So second point 1 here is 4 seconds, and point 2 here could be 10 seconds or something. And then we simply calculate rise over run, and we can find the average velocity of this curved line, or of this object that's slowing down. Now, what you should know is that the more the more vertical the line is, the faster the object is going. Now, let's look at this right here. At this point over here, if we draw another tangent line, uh, we can see that the line is more horizontal. So, more vertical. So it's closer to the y-axis than closer to looking like a y-axis line than an x-axis line. And the more vertical you get, the faster the object becomes, or faster the object is moving. Now, if you look at over here, if you look at this point over here at t equals 14, you can see that the tangent line is practically horizontal, meaning that the object is not moving, or it's in no motion. So no motion when it's a horizontal line, and the more vertical it becomes, the faster it will be. So the more vertical the tangent line, the more the faster the object is moving. And that's for the position time graph. Now in this case, we can see that the object is speeding up because as the more time it takes, or the longer it's in motion, the more vertical its tangent line is, or the more vertical. If I were to take a tangent line here, it's more horizontal, and here it's more vertical, and it becomes pretty fast around here. So we can see here that the difference between these two is that one is getting slower, or one is slowing down because its tangent line is, becoming less vertical. And in this case, the more time it takes, it's becoming more vertical, meaning that it's moving faster and faster. Let's look at this example here about position time graphs. So the first question here asks us at what time, so we're looking at time now, was the runner's position when it was equal to 20 meters? So 20 meters here. What time was his position? So his position was equal to 20 meters, and we're looking for the time. So we can go ahead and look here, and we find the 20 meters, and then we can just draw a line. It's already drawn for us, but draw a line here. And then we look at the x-axis, which is time, and then we find out that it's 2 seconds. So the position at 20 meters is 2 seconds. This next question, question B, asks us what was the runner's position at the time that's equal to 2.5 seconds. So now we don't have position. So position is unknown. So position is unknown. And the time is at 2.5 seconds. So we can do the exact same thing. We look at 2.5 seconds, so it's around in the center of 2 and 3. And then we draw a line straight towards the object's movement. And then we draw another line, and we can see that it's around half of 30, and it's in between 30 and 20, so around 25. So what's the position at time 2.5 seconds? It's around 25 meters. So 25 meters. Now, before we move on to the third question, question C, I just wanted to mention here that when referring to position, we should still mention the direction. So 25 meters. We could say it's 25 meters if this is north and this is south. In this case, you could say 25 meters uh, north east. So north east. Just to continue mentioning the direction as a vector quantity, so position. And finally, for the third question, what was the runner's displacement? So displacement from t is equal to 1 second to t is equal to 5 seconds. So we have 1 second and we have 5 seconds. So at t equal to 1 second, we can see here that it's around 10 meters. So at t equal to 1 second, the object is at 10 meters. So position 1, or we could say x1 or x initial, is equal to 10 meters. Now, the second position is t is equal to 5. So t equal to 5, if we draw our line here, we can see that it's around 50 meters. So so x final is equal to 50, so 50 meters. Now, if you remember the displacement formula, it says that delta x, so displacement, is equal to delta x final minus x initial. So if we just substitute both values, we can see that delta x is equal to 50, so delta x final, minus 10, which is equal to 40 meters. So what is it? So 40 meters. So what is the displacement? We could say the displacement is 40 meters from the origin, from t equal 1 second to t equal 5 seconds. Now we can also notice here that t equal 1 second is the reference point and not t equals 0. So we wouldn't count it from t equals 0, we count it from t equal 1. That's why position is relative to the reference point. Kind of question you'll encounter in position versus time graphs are when there are two different objects or two different instances in one position time graph. So for example, in this case, you have two people, Jonita and Heather, and they're both walking uh, at certain distance. So in this question, it asks us how long, so time, how long had Juanita been walking when Heather started her walk? So we want to know the difference between, so the delta t, the difference in time between Juanita's walk and Heather's walk. So if we look here in the graph, we see that Juanita started her walk at point t equal to 0. So the t of Juanita is equal to 0.0 seconds. And then we look at for Heather, we can see that her walk started at around t is equal to 0.1, not seconds actually, hours. Hours. 0.1 hours. So, how do we calculate it? Well, to find delta t, we do t final minus t initial. So in this case, Juanetta started first, so she will be T initial, and Heather started second, so she will be T final. So it'll be 0.1 hours minus 0.0 hours. So delta T is equal to 0.1 hours, which is in fact how long it took for Heather to start walking after Juanita. We can see after 1 hour she started walking and her line started moving up. Will Heather ever catch up to Juanita? This is our second question. Now, to be able to catch up to someone, you should logically be faster than the person. If you're behind them, for example, so if this person, this dot A is behind dot B, then for dot A to become in front of dot B, dot A needs to be faster or needs to be moving at a faster speed. So for this to happen, we need Heather to be moving at a faster speed than Juanita. And in this case, that's not the case. If we just calculate, if you wanted to calculate the average speed here, we would take rise over run. So it's like 0.5, or we can take easier numbers like t is equal to 1, t is equal to 2. So we do y1 minus y2. So we do 5.5 minus 2.5. So rise over run. So this is the average velocity of Heather. So it's equal to rise over 1, which is equal to 5.5 minus 2.5 over 2 minus 1. So 2 minus 1. So we get over 1, and then we do 2.5 minus 5.5, so we do 3. So the average speed here for Heather is 3 meters per second. And then if velocity, it's northeast, because here's north, here's south. Now, the average speed of Juanetta, this case, so the average velocity Juanetta is equal to, again, rise over run. So we can take 2 points here. Take point here, and we take point here. So we do rise over 1. So it's equal to 4 minus 2, and then 0.4. It's actually, it should be here. So 0.678. So 0.8 minus 0.4, and we get 2 over 0.4, which is equal to 5 meters per second northeast. So just by looking at the speeds here, we can see that although, even though Jonetta started first, she's going to continue to be first simply because she's moving faster. Remember how we stated before that for a person to be moving at a faster, for a person to surpass another dot, the one that's behind, so A and B, for A to surpass B, A needs to be moving at a faster speed. So in this case, Heather isn't moving faster than Juanita, thus she can't surpass her. Now, a case where she would surpass her is if we had runner here, runner C, and runner C was moving at a rate as such where her line, her movement line, or she's intersecting and actually surpassing Heather at this point, at point 4. Now, her speed is definitely more than 3 meters per second in this case. We can calculate it, but there's no need. We can tell immediately that an object or a person is moving faster just by looking at the line themselves. If the line is more steeper and more vertical, then it's moving faster than a line that is less vertical. So the less vertical, the slower; the more vertical, the faster. So this point right here is where uh, runner C surpassed Heather, and now runner C is in front of Heather, and is going to continue to be in front of Heather unless Heather speeds up herself. Now, the final questions we're going to go over are questions for related to position time graphs, uh, also in the negative and positive direction. So here we have a negative graph, so when it's going down, it's negative. When it's going up, it's positive. When left, it's negative. When right, it's positive. So knowing this, let's solve the first question. We need to find the distance between point A to point E. So point A, point E. So whenever it's distance, we ignore any negatives. We just add the distance. So from point A to B, it's 30 meters. Plus, we have point B to point C. It didn't move at all, so plus a 0 meters. And then from point C to D, plus 30 meters. Remember, we don't take any negative signs. And then from point D to point E, it's 20 meters. Now we add them up and we have distance traveled is 80, equal to 80 meters. So that's our answer for question 1. Now question 2 is asking for the displacement from point A to E. So in displacement, we will add the vectors and include negative signs. So from point A to B again, it's equal to 30 meters. From point B to C, it's equal to 0 meters. Did not move. Yes, whenever there's a straight line in a position time graph, it means no motion. So x is equal to 0 meters. Now from point C to D, it's going to be equal to negative 30 meters. Why is this negative? Because it's moving downwards, and whenever downwards, so whenever there's a downwards motion uh, in a position time graph, it's negative. So that's what's negative. We can also find it using the displacement formula. So delta x is equal to x final minus x initial. So delta x is equal to 30. So 30 is the initial and 0 is the final. So 30, 0 is the final. So 0 minus 30 meters. So we get delta x is equal to negative 30 meters. So we can use the formula, or we can just use the graph to get the values. Both work. So we have our final value. We want to find d to e. So if we want to use the formula again, we can. To x final minus x initial. So the initial here is 0 and the final is negative 20. So negative 20 minus 0, which is equal to negative 20 meters. So d is equal to negative 20 meters. Now when we find displacement, we add them. So 30 plus 0 plus negative 30, and then plus negative 20. And then we get 30 cancels 30, and the displacement, so delta x to x is equal to negative 20 meters. And we should specify the direction, so it moved around south or east of south, so east of south. The final question asks, at which points are there no motion? So from point B to C, there's no motion. It's a straight line. Okay, so for this final line here, they intersect. So when they intersect, it means that they're moving in either two cases. So one in a position time graph when they intersect from the same direction, so they're both moving like this, it means that one is surpassing the other. We saw this example earlier. Now, when one is moving over here in this direction, and one is moving like this, so one is moving in this direction and one is moving in this direction, it means that they are moving in the opposite directions. We can take a better look at this by drawing this in a position in a number line where x is the base or the numbers. So we have 40 meters here. So we look at starting positions at t equals 0 for both cases. So when a is 0 and h is 0, h is 40 meters. So h is here and a is here. So a is 40 and h is 40. A is 0 and h is 40. Now we're going to see here that h is going to move all the way to 0. So this will be line hg actually. And a will move all the way till uh, 30. So here till 30. So you can see here that they're moving in actual opposite directions where they're facing each other. So this is what you call face to face, where they're moving at the same in opposite directions. That will be it for lesson 2.3, position time graphs. If you have any questions or want to ask anything at all, you can ask it down below in the comments or in the server. If you want more tutorials just like this about physics or any other subjects, you can find them on the channel. And yeah, enjoy them.